All right, so today we're going to look at the second part of energy that we looked at yesterday. We started looking at kinetic energy. So today we're looking at potential energy. So we're going to be focusing, there's multiple types of potential energy. Potential energy just means stored up, right? Potential energy. Think of it as stored energy. So stored up, ready to go. So we have elastic energy, elastic potential, which we'll look at a later point. It's basically talking about springs, rubber bands, whatever case may be. Whether you stretch it or you squish it, and then it rebounds, right? That's elastic potential energy. We are going to be looking at today is gravitational potential energy. Okay? So it is energy potential, gravitational potential energy, all right, EPG. What that means is that as you lift an object up off a reference level, so if I take a weight and I lift it above the earth, gravity wants to pull it down. So all the work is being done by, so gravity is giving the energy. Gravity wants to pull it down. Remember we talked about last time, as it's falling down, it will speed up and it will gain kinetic energy. Where is that energy coming from? Well, it is being converted from potential energy. Remember, last class we talked about how it is, if something is being done, energy is being transferred. It's not being created, it's just being transferred. So gravity is creating the potential. So if an apple is up here in a tree, because it is so far off the ground, it has potential energy based on gravity. If that stem ever breaks, it falls down, and that's, you get kinetic energy as it's falling down. Okay, so it just has gravitational potential. All right. So how do we calculate that? The mass of the object times gravitational force times the height at which it is off the ground, mgh. Okay, and again, it is also measured in joules, like all energy. Okay, so we are going to use that formula to do a couple examples. It is pretty straightforward, just like kinetic energy was straightforward. Okay. Dry off the board. So if we have a 10 kilogram weight from the ground and we lift it up to 5 meters high, what is the initial potential energy? Well, if it's on the ground, gravity can't pull it any further down, so therefore it has no energy. It is just sitting there. So then, what is the final gravitational potential? mgh. So it is 10 kilograms times 9.8 times 5. So our EPG final is going to be 490 joules. Pretty straightforward. Okay, we'll do one more example. This is coming from a textbook, all coming from a textbook. It says a pendulum has a weight on it that is 500 grams, and it is on a 1 meter length. If we lift that up to 30 degrees, what is the potential energy gained by moving that up 30 degrees? Remember, as you move it up, it gets higher up. So all we have to figure out is what is the height difference between the original at resting and the 30 degrees up high. So the height difference is simply 1 meter minus 1 meter times cos 30, right? Because cos 30 gives you that difference, right? So 1 meter minus cos 30, because that's cos 30 right there, here, this part here is cos 30. So the difference is 1 minus that. And then once we have that height, that difference is 0.657 meters. And then we can simply go back to EP is equal to mass, which is 0.5 kilograms, times mg, 9.8, times 0.657, which gives us an answer of, oh, sorry, wrote the wrong one. This is 0.134, so this is 0.657 joules. Okay? So anytime you talk about gravitational potential energy, all you have to figure out is how far is it off your ground, your reference point, and how much does it weigh, and then gravity will do the rest. All right? Okay, so now the second part that we're talking about today, right now, is the conservation of mechanical energy. If, I'll write that down. So if we negate, if there is no force of friction, meaning no air resistance, no loss of energy in any way, shape, or form, then all of the energy that's in a system will remain in the system. Okay, so the start, the mechanical energy. Actually, I don't want to do that. I'll rewrite that here. The initial kinetic energy plus the initial potential energy must equal the final kinetic energy plus the final potential energy. So as the apple is falling, it starts out initially with 0 and all potential. As it falls, the potential slowly becomes kinetic, and this goes down, this goes up. However, at the very end, right before impact with the ground, all of this will become there. This will be 0, that will be 0. But the system balances out. It does not gain energy and does not lose energy. The example they use in the book is a skateboard ramp, and then you have a kid on a skateboard. So at the very top here, it is all potential energy. So as the skateboarder goes down, here at the very bottom, when he or she is at the full speed, that is all kinetic energy. And then when it goes back up here, we're all back to potential energy. So halfway in between, you get sort of half, right? Okay, the system does not lose energy. If it was a perfect system and friction doesn't happen, it does not lose energy going across that board. All right? So now let's do a couple examples with conservation of mechanical energy. It just means that all conservation of mechanical energy means is that whatever you have at the beginning, you should have at the end, because we're talking about theoretical physics here. We're not talking about real life application at the moment, because we're not calculating in resistance or friction. So if we have a 2 kilogram something that is at 10 meters high, okay, and then it starts falling, what will be the final velocity? So 2 kilogram weight, 10 meters high, let it go. What will this final speed be right before impact with the ground? Well, we have to figure out the energy. We know that at the beginning, it is all potential energy. And at the end, it will be all kinetic energy. But we know that it must be equal. So mgh must equal 1/2 mv squared. So if we have 2 times 9.8 times 10, must equal 1/2 times 2 times v squared. And then we can get our answer. V is equal to 14 meters per second. So if we drop a 2 kilogram weight from 10 meters high, by the time it hits the ground, it will be traveling at 14 meters per second. Pretty decent. All right? Okay, example B. Example B says, if an object is traveling at 5 meters per second when it is 50 meters off the ground. So we're already talking about something's already moving. So let's say it fell from a higher point, and when it's at 50 meters, it is going 5 meters per second. Okay? What is the final velocity when it hits the ground? So again, if we can capture a still frame in that point, at that moment, somewhere over here, 50 meters off, it is traveling at 5 meters per second. So we can calculate everything we need to know based on that. We have a still shot of what's happening at any point in the system. It means that we can find the overall energy. So we know that M, the initial, so at this point, we have to worry about the kinetic energy and we have to worry about the potential energy at this point because it's already moving and it still hasn't hit the ground yet. And we also know that this will equal at the very, very end when it's about to hit the ground. So kinetic energy at that point is 1/2 mv squared plus mgh. And at the end, it's just 1/2 mv squared. Do we know the mass? No, we don't know the mass. However, that's the only unknown way we have. So if we only have one unknown, we can leave it as is. So we can say 1/2 m5 squared plus mass, again, m, 9.8 times 50. So that's the point in time. That's what that is. At 50 meters, that's what that is. So right before it hits the ground, we have 1/2 mv squared. Now, if we do all of that, if we add that side up, we get 502.5 m, right? The m stays, the m stays. It's equal to 1/2 mv squared. Well, if we have an m on this side, m on this side, we can essentially cancel them out. So we have 502.5 is equal to 1/2 v squared. Now we don't no longer have the mass, we can figure out that the velocity is going to be 31.7 meters per second. Okay, so you don't really need to know the mass of the object if it's the same object that hasn't changed mass as it's falling through the air. You can figure out how fast it's going because you know how fast it was going at that point in time. All right, so that's it for today. Quick lesson.